As we start a new section, we're going to talk about an idea called parametric equations. And the idea is that a function, or the movement particularly of an object, is related to time. So let me jump ahead and kind of show you this here. Let me go to the graph. Okay, so if I graphed this equation, y equals x squared minus 1, I would get this shape here on the left. But what's happening in a parametric equation is this, that the movement is related to time. So what's happening in both the x direction and the y direction are related to time. So as time changes, the x and y are changing. And so instead of looking at this as just simply y as a function of x, what we want to see is that both x and y are the function of another independent variable. That independent variable is time. So if you look at this graph, they've left a little bit of this out here, but both x and y would be impacted by time. So how this object is moving depends upon the time at which it's occurring, but you can not only, when you graph it, you can also see a direction. As time is increasing, we can see that this object has moved in this direction and up to the right. So let me see if I can try to show this to you here. What we want to do to start with is we want to turn a function like this into something that depends on time. We want y and x to both be a function of time. Now, to turn a regular function into a parameterized function, we could do this multiple ways. But here they're giving us like the most basic that we can have. We're going to say, okay, the x's in this function are based on time. So when time changes, the x changes. So now what we've done is we've not limited it to two idle nodes. We now have a third one, a third variable called time. And that time is going to impact the other two. So we're saying that the position of x depends on the time. Now y we've already said depends on x, so let's change that one as well. If we're saying y depends on x and x depends on t, what we could say is, so if this is what x depends on, we could change those x's to t's. So again, what I'm saying here is that both y and x are going to depend on time. As time changes, x and y are going to change. So we've turned x into a dependent variable that depends on time in the most basic way possible. We're saying that as time changes, x directly changes. Now, if we want to change this function, how do we want to talk about y in terms of time? Well, if x is dependent on t, we can just substitute all the x's out with this function. And we're going to replace x with t, and so then it becomes t squared. Now, here's how we would graph something like this, a parametric equation. Instead of just having x and y up here like we normally would, and we would just plot points, we now have t, x, and y. Because t is going to impact not only x, it's also going to impact y. It's going to impact both of the other two. X and y both depend on time. So what we've said is that time, so we said x is identical to the time. So if time is -4, x is -4. If time is -3, x is -3. Now, we've also recreated this equation, so it no longer is dependent on x, it's dependent on time. And we would crunch this in the typical way. When time is -4, we get out, crunch it down, we get 15 for y. When time is -3, we crunch it out and get 8. So if we are graphing this, we're going to graph it in the typical fashion. We're going to do the point -4, 15. We're going to do the point -3, 8. But what's changed is we now see that there's a movement as we go down through time. They depended on the time. So that's these graphs we've already looked at. Here is what we normally would get. However, if we've made it dependent on time, as the time was changing, we're moving to the right. Okay, so let's do this again here. They've actually given us the parametric equations a little more complicated. They're saying that x depends on time, but it's in this way, t minus 3. And y depends on time, 2t plus 4. They're telling us we're going to go between -1 and 2. So here's how we could set up a table. So when time is -1, so it's like we're plotting points, but we've added this new column that represents the time. So times -1, 0, 1, and 2. Well, what happens to these now two dependent variables that depend on time? Here's what we get. Now we plot the points just like we always would. There's nothing unusual about that. We're just going to plot these points and we get this picture. Now here's what's changed, however. We have arrows indicating that as our time is changing, as time is getting larger, we're going in this direction. We're going upward. So basically we've made two independent or dependent variables instead of one, and we now see direction. Okay, once again they'd like us to change this into a parametric or to two parametric equations. So they're telling us make that basic switch. The most basic way you could do this is we're going to say x is dependent on t. Okay, so if we now change this equation, instead of x, we're going to replace it with t. So we have our two equations. We've said x is now dependent on t, and we're saying y is now dependent on t, and we just took the x's because this formula has gone right into there, what used to be an x. Okay, we plot points just like we always would, and we're still plotting the same points. We're still plotting the x's and the y's. Still plotting them. But we're also going to see an additional aspect of movement as t goes from the negatives to the positives. So here's our graph. As t is going from the negatives to the positives, we see this movement, and so we add these arrows to our curve. Okay, so they've left the choice up to us on how to parameterize this. Now, what we've been doing is we've been saying x is equal to, well, x is a function of t. We've been making that change. But if they're not telling us what to do, this is already set up where x appears to be a function of y. So let's make a different change. Let's make y sub t equal to t. Let's make this change. We're saying y is dependent on t directly, just like this. And so what we'll do is then we'll replace all of the values of y with t. Just the opposite change that we'd been making. And we did that just because x was already alone over here. And so the choice to parameterize these is open to us and to figure out a way to do that. So we went the other way and we create this. Okay. Yeah, this is a little complicated here. So I think a better way to do this, what they're saying is that there's this change going on between these 2 points, and it's parametric. We want to see that it's in relationship to time. What I think I would do here is I would just do a normal line. I could find the slope, x and b, just like I always could. Then what I would do is I would change this over to a parametric equation. Again, I think that's the best way to do it. Now, what they have done here, I'm just going to explain this to you. They found the changes that are taking place in the x direction with respect to time. So we went from -5 to 3 in 4 seconds. And so that we're going to treat that as a slope with respect to time. Again, there's multiple ways you could do this, and I would recommend you just find the line and do what we did before, where we're going to say, okay, well, x then is a function of time, and then y sub t would just replace, it would be mt plus b. That would be true. It could work. But what they're doing is they're finding the rate of change with respect to time between the two x's. They get 2. They're finding the rate of change with respect to time with the two y's, 3 and -1. Okay, so they've got now two slopes with respect to time. Do you see these are now slopes with respect to time? So x sub t has 2 as a slope, y sub t has -1 as a slope, and they took their starting position. Since it was related to time, the y's started at 3 to make that like a y-intercept, and the x's started at -5. Again, I think this is a pretty unusual question, and I like my explanation better, but that's what they've done. They found the slope, the change in the x's with respect to time, and the time was, what was it, 4 seconds. They found the change of y's with respect to time, which was -1, and those are rates of change, so they're slopes. And then they said, okay, well, I started at -5 in the x direction, I started at 3 in the y direction, and they've made two lines that are dependent upon time. So you graph those the same way. You just pick some points for t, but you're still graphing the values of x and y. The only thing that's happened is you get the direction. So you get the same graph here you would if you had just done y equals mx plus b, but you add on the arrows for direction. Okay, that's an introduction to parametric equations. Pretty simple. I think you'll see that it would be for the mapping of the movement of an object, big in physics, astronomy, something like that, where we want more than just the graph of the line. We see that both the x direction and the y direction are dependent on the passage of time. So y has always been dependent on x, but what we're changing now is we're going to make that x and y are both dependent on this third variable, time.